Hello and thank you for joining us. This is Team 1113 for the SIMIODE competition, and we are presenting Problem A, Introducing Stress. My name is Elana Cummings, and I'm here today with my two partners, Kelley and Elliot Cataldi. Thank you to our coach, Mr. Reece, for assisting us in this competition. The Problem A scenario took place in space. Astronauts were sent a second group of capable people who were not yet used to the environment to assist them with a series of tasks. Our job was to build a mathematical model of the stress levels and capability of the entire group with the intention of comparing the three different schedules. Based on our results, we must find which scenario results in the lowest stress and highest net productivity. In order to begin, we made a series of assumptions to make the problem easier to work with. Based on our research, astronauts can only work for 12 hours a day. They spend the rest of their time eating, sleeping, or exercising, as the decreased gravity in space can be very detrimental to muscle mass. We also assumed that the only two stressors were caused by the workload and new people, giving us an idea of the inputs of stress. The main methods of stress relief were not working or taking a break. We assumed that the capability at the given moment was only determined by stress, and that stress and capability have an inverse relationship. This assumption is based off the logic that the more stressed someone is, the more they overthink and the less they can get done, so they are less capable. We also assumed astronauts will follow the given schedule. They're all trying to do the work when they are supposed to and not trying to work instead of sleep or some other variation. The original deadline for the trip was 8 days, so we assumed all tasks should be completed within 8 days. In the actual scenario, they extended the deadline. However, we wanted to know which schedule would be done in a given time frame. We also assumed that all people function the same and have the same capacity for stress. We treated the group as a whole instead of nuanced individuals. And finally, the second group got used to being in space, and the amount of stress they caused to the first group decreased.
After making our assumptions, we had to create the models. We created a differential equation to map stress. This model was based off of the money differential equation model. There is a rate in which stressors are causing stress, and a rate out, which stress is dissipating. In order to take capability into account, we also created a capability equation based on the population logistic differential equation. In order to contextualize the equation, we first started by determining the rate out. The rate of diffusion, some constant, multiplied by the amount of hours that the astronauts were not working, would equal the rate in which the astronauts are getting less stressed. The hours of free time, of course, would depend on how much work they were doing. In order to take this into account, we created a function for busyness, or the amount of work per hour that needed to get done. We subtracted the hours of work from hours in a day and divided by hours in a day in order to get the stress at that moment. The rate in was a little more difficult and depends on two functions. First is the busyness graph, which would be based on the schedules given. The second is the rate of stress caused by new people. The rate of stress caused by new people would decrease over time, but started out quite high. Then we have our capability equation, which gives us the capability of the individual based on their stress level. We theorize that the individuals only have a certain capacity for stress, and after they pass a certain point, they become too stressed to continue working. The graph here shows capability and stress graph. Finally, our last equation is N of T, or the amount of stress caused by the new people. We decided the amount of stress they caused would be 50 out of 100, and that they would finish adjusting by the time that 8 days had passed and the mission was over.
Now it's time to take the schedules into account. The first schedule given to the astronauts expects that they are extremely productive in a very short amount of time. This would mean that their rate of busyness is extremely high. For this to work, we created the busyness function. They would be busy for 8 hours a day in this scenario, so in this case, the busyness function was constant. Then we decided on some constants for our equation. According to the original article this scenario is based on, the original mission was supposed to take 8 days. The amount of people in the mission was 12, making the total workload 8 hours a day multiplied by 8 days times the amount of people for 768 hours of work in total. We kept these constants the same in all of our schedules. We then graphed our results here by combining the equations into one large stress equation. As you can see, the amount of stress at the beginning is very high, but as time continues, the individuals are less and less stressed.
The second schedule consists of a short rest, then immediately afterwards an increase in expected productivity. B of X has changed to better fit the busyness requirements and the total expected productivity. On the first 2 days, they did not work at all, and on the third, they worked for 4 hours, and every day after that, they worked for 12 hours per day. Everything else remains the same. We have graphed our results here. As you can see, the stress is steady and low at first, and then shoots up when the workload begins. However, it begins to decrease as time goes on.
The final schedule consists of a slow increase of work expected. We interpreted this as B of X equals 2x, increasing the workload as time went on. We graphed the results of the final schedule here. The amount of stress is low at first, but increases and peaks a little before half of the days are over. Then it decreases back to zero stress.
Now that we've graphed the three schedules, it's time to decide which one was the best. Taking the integral of our stress functions, we found that the total stress was the smallest in Schedule 3 by a mere 0.156. The second schedule quickly followed, and the first schedule was the most stressful of the three. In order to calculate how much work was accomplished, the capability graph received data points from the stress graph. Those capability points were multiplied by hours worked per day, then multiplied by the number of people, and finally added together. It concluded that Schedule 1 accomplished 62.8% of assigned work, Schedule 2 accomplished 64.4%, and finally, Schedule 3 got 82% of the work done. While none of the schedules managed to complete the amount of work within the time frame, the most amount of work done and the least amount of stress felt was in the third schedule. Thus, we can safely conclude that the third schedule was the best. Now, what were the strengths and weaknesses of our model? Our model could work for different numbers of people, different amounts of work, and different requirements for hours of exercise, sleep, and free time. It is also customizable for individuals. By adjusting the L and D values, the model can work for an individual's capacity for stress and diffusion rate of stress. Because there are so many variables, it can take many different issues and differences into account. However, there are some limitations. Due to time constraints, we had to simplify our model quite a bit, but in reality, stress is not money. To accurately model human stress, we would have preferred to have done some research into the human mind to accurately see how stress truly affects capability. We also did not take into account individuals and simply viewed the group as a hive mind, and did not take into account what tasks were being performed, simply how long it took to do those tasks. That's all we have today. Thank you for joining us. Here are our sources.